Uh, let's see how many audience I got. Can't see it. Okay, ladies and gentlemen, welcome to this afternoon's technical talk. We have with us Associate Professor Dr. Dominic, Engineer Dr. Dominic. He's actually an Associate Professor in the Griffith University in the Brisbane, is it? The city is Brisbane?
Yes, yes.
Brisbane, Queensland. And the topic he's going to give is now on your screen, geotechnical behavior and interpretation of reconstituted geomaterials for soil structure applications. But before we start the talk, let me read his CV. It's quite an impressive CV. Sorry, I have to read it from the phone.
Thank you, Prof. Tan.
Yeah. Okay, just give me a few minutes. Okay, Associate Professor Ong is a graduate of the University of Western Australia. That's Perth, further.
Yes.
And the National University of Singapore. So your PhD from Singapore, eh?
Yes.
PhD from Singapore, okay.
Correct.
He's an acclaimed expert in geotechnical engineering, specializing in underground space technology and geomaterial science, involving deep excavation, tunneling, pipe jacking, and ground improvement, among others. Sorry, my phone keeps switching off. He has local Malaysian, Singaporean, and Australian consulting experience of 25 years and was previously the Director, Research Center of Sustainable Technologies in Swinburne University. Now, Swinburne University is actually an Australian university, but this was in Sarawak, a branch in Sarawak. Okay, Associate Professor Ong is a fellow and a professional engineer of both Engineers Australia and, of course, the Institution of Engineers Malaysia. He's also a senior fellow of the Higher Education Academy, UK. Besides being the co-editor-in-chief of Geotechnical Research, wait a minute, a journal of the Institution of Civil Engineers, ICE, UK, he's also the associate editor of Frontiers in Earth Science. So there's more geology, Frontiers in Earth Science Journal. Okay. Associate Professor Ong is an expert member of Technical Committee TC104, Physical Modeling in Geomechanics, and TC207. TC207 is soil structure interaction and retaining walls in the International Society for Soil Mechanics and Geotechnical Engineering. And this society has a lot of technical committees.
Yeah.
Okay, for the period 2013 to 2022, or 10 years, he was the world's top 12 researcher in geotechnical research in incorporating trenchless technology and pipe jacking. This is a kind of specialized field.
Yep.
Trenchless technology and pipe jacking. He was the lead author of the book Sustainable Pipe Jacking Technology in the Urban Environment, Recent Advances and Innovations, 2020, publication, 2022, and editor of another book, Soil Structure Interaction 2023. Finally, in June 2023, Associate Professor Ong and his research team won the ICE's Telford Premium Prize for their impactful paper on ground improvement. This prestigious prize is awarded to recognize key papers across all ICE journals. So this is a very prestigious award. So our friend Dr. Ong has done very well. He's still very young, but he has gone very far. So, okay, with that brief introduction, can I, Dr. Ong, the floor is yours. Yeah. Okay, just a reminder, 1 hour presentation, and then we have another 30 minutes for Q&A. Okay.
Sure. Okay. First and foremost, I'd like to extend my sincere gratitude to Professor Tan Boon Kong. I think I still greet him as a professor because he, in a way, inspired me to, when I was young, when we were working on certain projects, to actually embrace a very practical approach and mindset in developing our career. So even though I'm a geotechnical engineer by training, But nowadays I deal a lot with rocks. And if we look at the geology in Sarawak, I'm a Sarawakian. I'm from Sarawak. I'm now in Kuching, visiting my parents. And we actually do know that the in general rocks in Sarawak are rather relatively young as compared to the more established geology of in West Malaysia. So when we come to any construction involving roads where we have a lot of cuts, where we are building dams, so it gives us challenges. At the same time, it gives us opportunities to actually use and also our knowledge and push boundaries to see how we can actually live with materials that are not perfect. And in any case, I'm also obliged to actually mention that in the field of geotechnical engineering, and I believe in the field of engineering geology, we actually deal with a lot of naturally occurring materials. Unlike my counterpart in structural engineering, where they deal a lot with man-made materials like concrete and steel. So the challenge of working with naturally occurring materials like soils and rocks always give us that challenge, and I also say it also gives us opportunity to learn more. So even though I started my career as a practicing engineer, but my love for research has put me into the university environment, and also having the experience to still being able to do consulting. So today, I think it's more towards a sharing session that I'm happy to extend my knowledge in terms of using geomaterials. When I say geomaterials, it will be probably a bit of soil, a bit of rocks in engineering application, especially in this field where I call it soil structure interaction. So what is soil structure interaction is basically when your soil material actually deforms, or when it's actually impacted by load, and then it would actually respond to that load application and act on to the structure that you have actually just constructed. So the soil behavior on the structural behavior is very important, and I find great pleasure in trying to understand this complex interaction. So today I'm going to speak on geotechnical behavior and the interpretation of reconstituted materials for soil structure application. And I would like to thank the Institute of Geology Malaysia for this invitation. At the same time, also, I'd like to acknowledge all my past graduate students. As you can see, the work here that I'm presenting is actually an accumulation of 4 PhD work and also 2 Masters of Engineering work from the period of 2013 to 2023. Some of my students were from Swinburne in university. Swinburne University is an Australian university with presence in Kuching, and also up to today in Griffith University in Queensland. So my sincere thanks, and I'd like to also acknowledge their work that I'm using here to share with you. So I also like to point out that this book is a lot of sweat has gone into this book by the 6 authors, as you can see there. I was the first author. We produced this book when it was actually during the time of COVID. So we have a bit of time, and we pull all our experience together across the globe in 6 countries that we've got case studies in this this particular book, where we talk about how we actually do trenchless technology. Trenchless technology means you do not excavate a trench. That's why it's called trenchless technology. Basically, we do pipe jacking, we do micro tunneling, we do directional drilling to pull pipes in the ground without having to excavate a trench and then bury your pipe in the trench. So this is very effective, especially in Kuching. Later, I will show you a case study where we have the deep tunnel sewage system, and also in Singapore, where we actually transfer all the sewage underground up to about 50 meters and let the underground pipes take all our sewage from household to the wastewater treatment plant. From the wastewater treatment plant, the collection system would actually pump all the waste up to the treatment plant, and then we process it until you have achieved quality discharge, and then you discharge it into the river. So this book deals with a lot of challenges we face in constructing the trenchless technology using pipe jacking method in different geologies in 6 countries. So our book was published in 2022, and it has since been downloaded about 1,800 times since. So it's about 100 purchases a month. So you can actually Google this book if you are from the academic line. I think the university library usually should have a license for you to actually download for free. So the outline of today's lecture would be a bit of an introduction to the problem statement, what motivates us to actually embark on this research and working with the industry in driving trenchless technology or even characterization of geomaterials more accurately so that we could actually use it in engineering application. So I will introduce to you some technique that probably in the future, if you think that you have got geomaterials that you want to characterize so that you can use a most basic more Coulomb model to model some rock behavior or source structure interaction, then you can actually consider using the power law or the generalized tangential approach. And at the same time, also I will be presenting 2 case studies to validate the power law as well as the generalized tangential approach to let you see that is indeed applicable to real life projects. Like the first case study will be on pipe jacking, and the second case study would be on a stone column material. And also, lastly, I would like to also share with you in terms of our university ongoing research on granular geomaterials, looking at high performance cloud computing, discrete element modeling, 3D printing, and opportunities for new research. So what motivates us to actually embark on this kind of a work that not many people are into? Because in Sarawak, we are in a way blessed with challenging geology. And this is the first time when we dig so deep in the heart of the Kuching city, because before this, there was no excavation underground that has been done in Kuching city. And suddenly this project comes about. It's a deep tunnel sewage system in a way, that we have to dig up to 650 or excavate or even tunnel 50 or 60 meters into the urban area. So we are seeing all these materials for the first time. So that's why we have opportunity to strike collaboration with industry to support our research. Now, the problem statement 1 here, I put it simply as the most analytical techniques are reported for tunneling drives traversing soils and not soft rocks. Now, this tunneling, I do not actually mean the rock tunnel that in the has done a lot, but this is more micro tunneling, which means your tunnel boring machine probably ranges between 1 meter to about 2.5 meters. So it's relatively small, not comparable to the rock tunnel or the rail tunnel kind of diameter. So because that the deep tunnel sewage system, most of the time in other parts in West Malaysia or Sabah, not so much in Sarawak, they have actually done it as shallower in the ground, something less than 5 meters, less than 6 meters. But this time in Sarawak, for the first time, we are going into like 50, 60 meters. So that gives us the opportunity to work on rocks. If you are less than 6 meters, probably you are still in soils. You are still in stiff soils, hard soils, but or probably not in rocks yet. So that is why it's in a way, it's almost unprecedented that we are working on this kind of geology. Now, so we are working on soft rocks. Why I say soft rocks is because these are the kind of rocks that if you look at problem statement number 2 there, in Kuching City is dominated by a metamorphic rock called phyllite. And if you were to drill phyllite using the conventional drilling, diamond core drilling, then you get the rock quality designation that is predominantly 0. So in a cumulative runs of 206 meters, we have obtained 155 meters, of which contribute to the RQD as 0%. So do you actually call this weak rocks? Because from the photo that you see down here, the rocks are definitely does not look weak. The rocks are heavily fissured, but in compression, under the confining pressure, the rocks are not weak. It's just that when you core through all this material, the fissures open up because of your mechanical drilling, then the fissures will start to crumble, and then when you extract all this, is actually RQD is 0. So if you have this kind of a rock as a soil mass, you would think it's strong, but when you extract it, it's RQD 0. So we are worried of the misconception that it will portray, and hence the client wanted us to study a little bit more about this metamorphic phyllite. So there's from the literature, you find that there's insufficient or inaccurate strength characterization. So this gives us the opportunity to do research. Now, in this problem statement 3, I call it, if you were to look at the tunnel that was created from the tunnel boring machine, the tunnel boring machine had to be pulled out in this particular instance. So it gives us the opportunity to look at the tunnel that we have created. So as you can see, the rocks are being, despite the rocks being highly fractured, but the tunnel can self-stand, and there's clear demonstrable strength despite the low RQD. So this creates a bit of motivation why the rocks as a soil mass is actually looks strong. It can self-support, but when you extract it into the ground because of the prevalent fissures, then it just crumble, and then you get RQD as 0. So in that kind of a situation, how do we do a engineering design, or how do we interpret the strength, and how do we advise the client on how to progress the micro tunneling works? So that serves as the research question to us to start off. If we were to look at this desert structure as such, if we were to say that, look, in conventional geotechnical engineering, if we have a cohesionless material and we have got this side slope here, that it has a typical angle of repose, or your internal friction of angle, it has a certain value, so that you can actually have a slope, so that the slope can be sustained, and at the same time also to what we have always been taught in the university, that if it's a cohesionless material, so your cohesion typically will be 0. So in this kind of a situation, yes, it probably describes what you actually see. But what about the part of the vertical upright structure right here? So how do you actually define rock strength parameters like C' and phi' to characterize this part where it's upright, where it has the strength to actually sustain itself? So this gives us the motivation to find answers too. So what is the C dash and what is the phi dash to describe this structure? By no means is weak, because it's been standing there for a very long time. So if we were to look at the micro perspective, and that's where we decided to look at the geoparticle characterization, and I call this the micro perspective. And as mentioned, this highly fractured phyllite with RQD of mainly 0. The rock course actually looks strong, but it has very poor RQD. So under the microscope, the phyllite spoil, this is how it looks like. It's pretty jagged, pretty sharp edges. So because the construction works are progressing and the research is actually ongoing. Okay, so it doesn't mean that we have the opportunity to learn about the rocks first and then try to apply it on the project, but it's like more like research at the same time when the project is running. So at that particular time, tunneling has started. Just to share with you, the tunneling was started by the Japanese, and then the Japanese would transfer the knowledge to the local. So because of the RQD 0, the Japanese created a tunnel boring machine that would actually grind through the so-called soft rocks. So to their dismay, they find that these rocks in compression is very hard. So they have to rebuild and modify the tunnel boring machine, because to them, they saw that RQD is 0, so they thought the rocks are actually quite weak. So when they have a suitable, at that time they thought was a suitable tunnel boring machine cutter face, they put it into the ground and they try to cut through this material. They found that it's quite hard. So you have a hard material in the ground, and then you have RQD 0 on your soil investigation report. So this is where us as the researchers came in, and then we wanted to start from the very beginning to see how we could actually use the tunnel spoil, which means the tunnel has actually gone through, it comes up with the spoil, and then how we could reconstitute rock samples for direct shear testing to actually explain the equivalent strength parameters. So this is the rock spoil that we were talking about. So the rocks was actually crushed by the tunnel boring machine, and then it's actually brought up to the surface. So pipe jacking drives were carried out across various geology, and mostly in the phyllite, metamorphic phyllite, and also the sedimentary shale, and it's collected from the descender. So we obtain materials like this. This is the tunneling spoil from sandstone, from shale, and grauwacke, and all are poorly graded sand-sized rock spoil. So under the magnified images, this is what we actually see. We can see that sand, obviously, you can see a bit more sphericity in terms of their shape as compared to the angularity in terms of the metamorphic, and in terms of the more to the sedimentary rock type. So we only have this rock spoils that we got from the tunnel boring machine, and then what we do is that our motivation is to reconstitute it back into that kind of a what they call it, a shear box. Okay, reconstitute it back, apply the same confining pressure as where the tunnel was, apply that same pressure, and then we try to shear it. Because by shearing, we would get the opportunity to see the C dash and the phi dash, which is the rock strength parameters. So conceptually, this is what's happening in the machine here. Okay, so one part of it is stationary, one part of it is actually moving, so that it creates a shear interface. And then from this shear interface, you can actually study the shear stress and the against the horizontal displacement to see the more of a granular material, you would have a bit of a peak. More of a clay material, you would have a flat plateau. So bear in mind that even though these are geoparticles of sand size, we have to sculpt under the ASTM standard. We are allowed to actually, and the Australian standards as well, we are allowed to actually sculpt the material so that the distribution is correct when it goes into the shear box. So there's a lot of work being done here. You can actually check my Google Scholar on the research that we do. But to cut short on the technical part, I just want to stress that as geotechnical engineers, we often see that there is always a non-linear behavior of soils and rocks. So the challenge when you have a non-linear behavior, as you can see in the smaller stress region to the high stress region, as you can see, if you try to put a straight line into it to derive the C dash and phi dash in terms of the Moore Coulomb model, is very difficult because it has a obvious non-linear behavior. So as a geotechnical engineer, we would actually need to define the strength parameters. So strength parameters, C dash and phi dash using the Moore Coulomb model would require a straight line. So with the dots like this, how are we going to force a straight line through this? It's not easy. As you can see, it is actually defined by a bit of a curve. And to talk about the jacking force model, because when we do pipe jacking, we would use a jack to actually push the pipe, the prefabricated pipe of 3 meters. It's like a culvert. You put it in the ground, you jack it forward, and then you jack more forward. And then over time, as you try to jack forward with a TBM face in front, you would encounter a force, a jacking force. So that's why we use a jacking force model to try to evaluate the vertical stress acting on your tunnel. So this is an important parameter here. So I wouldn't want to talk too much about this model, but this is how, as engineer, we would want to assess what would be the force required to jack your pipe across the ground. Okay, so that sigma EV is actually talking about the vertical soil stress, because of when you make a tunnel, the stress would redistribute within the ground mass. So when the rock actually redistribute, then some part of the vertical stress is carried by the rock through arching effect, and some part of it is actually not. So there is a distribution across the rock mass. So this equation, we find it very useful, is because it's mathematical. You can put numbers into it, and then you could actually estimate the effective vertical stress. If this number here, after you're putting in all these numbers, gives you a positive, which means there's no arching. If it's negative or close to 0, it means there's a significant arching. So arching is what we want to actually look at right there. And at the same time, if you notice, this equation requires the cohesion, and then it requires the friction angle. So because of that, this gives us the opportunity to actually obtain the C dash and phi dash from the direct shear test that I just talked about. Now, so most existing jacking force models, and in fact, most engineering geotechnical models that we use in the industry is actually the Moore Coulomb, which technically has the C dash, the cohesion, and the phi dash, which is the friction angle for the linear Moore Coulomb criterion. So it's intended for soil drives, and we do not have much information on our rocks. So that is why we actually embark on this research. And at the same time, also research has actually, literature review has actually shown to us that there is a concept of using the power law. So this power law, if you look at it, if you were to plot your shear stress on the y-axis against your effective stress your effective stress, that's right, on the x-axis. Then this is, oops, okay, your shear stress on your y-axis. And then this one here is your x-axis, your effective stress. So if you know your shear stress and if you know your effective stress, and then power law says that you could have a coefficient and then a B that is a power to the effective stress. So it's just as simple as this, that it will help you to define the curve. So the challenge here is to find what A and B parameter would actually fit into this curve fitting exercise to make that it goes through all of the points as required. So if we can actually put a curve like this case in the red curve for the circle and the blue curve for the triangle, then we can actually develop the A and the B coefficient. And then after that, we could actually use the C dash and phi dash. We can determine that. And once we know the C dash and phi dash, we can calculate sigma EV. So once we actually calculate sigma EV, we can put it back into this equation, and then we can calculate the jacking force. Or if you have the jacking force because it's measured on site, then we could actually use the information to calculate what is the coefficient of friction. Okay, so coefficient of friction for pipe jacking is very important because it determines how much friction will develop between the concrete pipe and the surrounding soil. So that is the reason why we want to try to fit the curve through all the points and not some of the points. So if you were to look at this power law, it has been used in many case studies as early as 1977. For rockfill materials, you can see sandstone, slate, basalt, conglomerate. So A and B parameters are actually quite established. So in our case, we are presenting a material for the first time from Sarawak, the metamorphic phyllite. And then if you were to look at it, phyllite and shale. So if you look at it, our parameter as such for A and as such for B is not too different from what other researchers have found. So I've got another case study here. If we have sufficient time, I will also explain to you where we use the material to characterize 75 millimeter aggregate stones for stone column design. Stone columns are basically piles that we put into the ground and replace the soft material with the stones, so that the ground is actually stronger. So I did a lot of work on this, and even though it's a microtonalite, which is a granitic rock in nature, you can see that the parameters A and B are actually quite comparable. So this gives us the confidence that this technique is really, really practical, and it actually helps us to validate our research work as well. So long story short, it takes a PhD to actually work on this, to actually characterize, to calibrate, to check against the field results, check against everything. So this is a summary of it. So we actually use the A and B parameter using the power law here. We could actually calculate the C dash, the equivalent C dash, and the equivalent phi dash. So this is the magic number that we need to put it into the Mole Coulomb model. So it takes a PhD student to actually prove that this is validated. So this is a long story that I fast forwarded to today to share with you what we have actually achieved. Okay, so don't worry about this, because in geotechnical engineering, we have the peak friction and we also have the residual friction. So you see the subscript P means for peak and then R means for residual. So we get two sets of parameters for our engineering use. So this is the real results. It's all been published in the American journal. So you can actually Google me, and then you can find the certain topics that you wish to have a more understanding on it. So as you can see, the best fit line, we look at it, what are the parameters and all. So on the next slide here, I just want to explain to you how this can be done. So in the future, if you have a very complex material behavior, non-linear, and you want to simplify into equivalent linear property, you could actually do this method, and then you could use back into any molecular model. So basically, this is how you do it. Now, in a stress strain plot, basically you need to find where your effective vertical stress is. Say your tunnel is actually 10 meters in the ground, and your unit weight for the rock, or maybe let's say for convenience sake, we just say it's 20. So 20 kilonewton per meter cube multiplied by the depth of 10 meters. So that gives you 200 kilonewton per meter cube, or 200 kPa. So that is your tunnel depth, and that is the pressure, that is the pressure experienced by your tunnel at that depth. So you start from there. So from your graph, you must look at that particular pressure at 200. And then once you have actually fitted the curve using the power law parameter A and B, as in this black line here, and you know that 200 is what you want, that's where your tunnel is. And then you just draw the vertical line up. It intersects the tangent. T, subscript T means is tangent. It must be at the tangent of your curve that you have fitted. And then you draw your red line, and it will intercept your y-axis. So this intersection of the y-axis is your equivalent cohesion. So once you get the equivalent cohesion, and then you get the equivalent friction angle, this gives you the interpreted C dash and phi dash. So it's as simple as this. Okay, so once you got your interpreted C dash and phi dash, put it back into this equation that gives you the effective vertical stress. And then once you actually have this equation, okay, you can actually put it into whatever equation that you will need to calculate. For my case, I use this to calculate the friction. We can know the jacking force because it's measured by the contractor, but we do not really know the friction coefficient. So this gives us the opportunity to back analyze and see what kind of a rock that would allow the lubricant to seep through the rock, and what kind of a rock that does not allow lubricant that we use in tunneling not to seep through the rock. Okay, so if your tunneling is actually lubricated, then your pipe jacking forces will be small. That would be our motivation. So this is also the relationship. If you do not want to work it out from the chart or from the graph, you can also calculate your C dash and phi dash, your equivalent C dash and phi dash using this equation, which is the equation taken from the graph. Okay, so with this, we would actually be able to address the non-linearity of the rock behavior and to put it into a workable model that we want to use. Okay, so now I want to validate whatever that we have postulated using the power law, the AB parameter, and also the tangential method. How reliable is this? So we have the perfect situation to actually perform a case study on this. So I call this macro perspective. So from the understanding of geoparticle, putting it through the established lab tests, through the direct shear equipment, and then using the right method to interpret the behavior, now we put it into practice and see how we perform. Okay, so this is the main project that we work on, the Kuching wastewater management system. It's a 20-year master plan to sewer up Kuching city, because now a lot of the individual septic tanks, if the buildings are old, the septic tanks are not maintained, all the sewage will go into the drain, from the drain to the river, and then it would pollute all the river. So the Sarawak government intends to sewer up all the heavily populated area to bring all the sewage into the wastewater treatment plant for treatment. So as you can see, there are now we are at Kuching wastewater phase 3. In Miri is phase 2 is coming. So major cities would have a master plan on this. So as you can see, there are kilometers and kilometers of pipes or sewer lines that we do trenchless technology. We install them using trenchless technology that varies from 1.5 meters all the way down to only to about 225 millimeter diameter. So look at the kilometers. There are many, many kilometers to serve the whole city area. Okay, as you can see, because they are isolated septic tanks, so we have to connect all the houses, septic tanks. You backfill the septic tank, and then you connect the individual houses sewage system to the master trunk, and then it would bring all this to the treatment plant. Okay, so this is basically to show you the difference between pipe jacking and also the rod tunnel. On the left-hand side here is actually large TBM for rod tunnel. On the right-hand side here is actually micro tunneling. As you can see, you build a shaft, you lower down the precast pipe, you put the pipe into the ground, and then you have a tunnel boring machine in front here, and then you have a jack, the jacking station. So as the tunnel boring machine here will grind through the rock, you provide the necessary push, and then you just connect the pipe every 3 meters, every 3 meters, every 3 meters. So you bring this pipe through the ground to your reception shaft. Then the reception shaft, you actually retrieve the tunnel boring machine, and then you will have a pipeline. And then you keep on doing this. You have a sinking shaft or the launch shaft, a reception shaft, and you keep on repeating this until you have a pipeline that crisscross the entire city. Okay, so what is the main difference between the large TBM and the small TBM is that in the large TBM, as you can see here, in between the tunnel and the precast panel, you would have the grout. So there is a perfect contact between the rocks and your concrete panel. Okay, in this case is the large tunnel, but in the smaller pipe jacking method or the micro tunneling method, there is no grouting, but they have a bentonite suspension or lubricant. So through the pipe, they can actually inject under pressure lubricant around the tunnel to lubricate the tunnel, so that your pipe jacking can be carried out without much friction between your pipe wall and the surrounding geology. But at the same time, it depends on what geology you're in. If you're in a geology that has a lot of fissures, okay, the bentonite can be lost. If the bentonite is lost into the fissures of the rock mass or into the fractures of the rock mass, then your pressurized lubricant is not effective. Then your pipe will sink to the bottom of the tunnel. So when your pipe sinks to the bottom of the tunnel, this is where you have the increase in pipe rock contact, and this causes the loss of buoyancy, and because of this, you have the friction. So that's why I said this friction angle here is the key parameter for geotechnical engineers to actually estimate. So in a rock that allow a lot of seepage of lubricant into the ground, you're going to have a high friction angle. In a ground that is actually can maintain the water tightness of the lubricant, then you're going to have a low friction coefficient. So the effectiveness of the lubrication for micro tunneling is actually very important, because if you have less friction, you can jack further. If you can jack further, then you do not need too many construction of the shaft. One shaft is about 1 million ringgit. So if you can save one shaft and go on a longer drive, then you are saving money for the client. So from this exercise, we see that we have jacked through. The white portion here is rock. The colored portion is all the overburdened soil. As you can see, a lot of the pipe jacking works here are done in rocks. That is why this is the first time that we do micro tunneling in mainly in rocks in Malaysia at that time. So if you to look at this phyllite, okay, in comparison to sandstone. Now, the direction of the jacking is this way for phyllite and this way for the sandstone. And as you can see, the lubrication used for phyllite is very low as compared to the lubrication for sandstone. And then if you were to look at that, the jacking speed for phyllite is very high. Then the jacking speed for sandstone is very slow. So if your jacking speed is very slow, it shows that there's a lot of interaction between your ground and your pipe. And then if you look at the jacking forces, in phyllite, the jacking forces are very small. And the contractors love this because there's less friction, there's less jacking force. But if you look at sandstone, in sandstone, the jacking forces is so much higher, and it takes a very long time to actually drive through sandstone as compared to phyllite. But at the same time, from the earlier part of the lecture that I just mentioned, phyllite gives you RQD at 0, but it can sustain the tunnel. And because it can sustain the tunnel, you have low jacking forces. You see, it's actually contradicting. So is phyllite such a bad material that gives you RQD 0? That is the $1 million question. From our research, it shows that phyllite is a perfect material for tunneling. But during the site investigation, it shows that RQD everything is 0. Why is this? In our research here, you see your jacking force is very small, your jacking speed is very high, your lubrication use is very low. It's a perfect condition. So it's watertight, it can form arching, and then you can increase your pipe jacking rate. Okay, isn't this, that's why I put a question mark here, isn't this contradicting? We said that RQD is 0, but why are we getting such good performance when we jack the pipe through phyllite? You see, so we are trying to explain this technically, and this is what we are showing here. Now, because if you were to look at this, this is the behavior of phyllite. Now, even though phyllite has a lot of fissures, but in an overburden pressure in the ground, the fissures are tight. Okay, and they are also because being metamorphic, they are folds. They are fissures, but under compression is tight. But for shale, it's actually laminated, like a bedding, you know. So you have bedding planes. So it has a preferred weakness plane, and it has a preferred path where lubricant can escape. So if you were to look at this, phyllite experience a lot of leakage from the tunnel. The lubricant cannot be sustained. You keep on pumping, and you lose the lubricant. And we put here shale in. It's also noted in sandstone. Okay, because in this previous one is sandstone, but in this one here we show that it's shale, but we actually notice the same behavior for it in sandstone. You have a lot of losses in sandstone, but in terms of our phyllite, you see, it has a water tightness. Okay, all the fissures that you see in the photos earlier on during SI, because these are all broken up when you send a mechanical drilling bit into the ground. But as a whole mass, phyllite is very good. So that is why from this understanding, we actually encourage the contractor to do an in situ pressure meter test instead of drilling through it and to obtain a rock core. So the contractor listened to us. That's why we could be, over the next research project, we managed to do pressure meter tests rather than drilling through the rocks. So that is the lesson learned. But more technically, if we look at this, because of the water tightness, we can actually achieve only a very small friction coefficient. If your friction coefficient is very small, according to Stein, 1989, you know, you have a well lubricated drive, and then your jacking force will be very high. So in this particular case here, the friction coefficient is very large. So if your friction coefficient is more than 0.3 as defined by Stein, it shows that your tunneling works here is actually under a very low lubricated behavior. And then that's why you register a lot of jacking forces in this case. Jacking speed is slow, jacking forces are high, you have to use a lot of lubricant. Okay, sandstone or shale has the same behavior. So this gives us a lot of understanding and try to explain the situation to the contractor, because at that time, like what I said, this is the first time that we go so deep in Kuching City. So in summary, the influence of surrounding geology is very important. Whether you're in phyllite, you're in sandstone, you're in shale, is very important to understand the pipe jacking behavior. And the influence of the equivalent soil strength is also very important, because when we do the design, we have to do a forward prediction. okay, from the understanding that we learn, okay, we know the C dash and phi dash. Then in the second stage of this research, we will be able to predict. That's why we do the design. Okay, but what we actually do in the first stage of the research is that we back analyze to understand the concept. Then in the second stage of the work, we try to predict. And with the method that we have developed, we are able to predict how far the drives can be based on the geology. So that makes the contractor and the client very happy, and that actually opened the floodgate for our journal publication. If you can check my Google Scholar out, you can see a lot of work I've done on pipe jacking. And at one point in time, over that 10-year period, our team was the top 12 most productive researchers in this field. This is actually measured through Clarivet. I think you also, if you're a researcher, you know that Clarivet is a very reliable metrics that we use to measure the impact of our research work. So I would actually dare say that our group were the first to actually propose this method to the world, how we actually can test and measure and quantify and validate the whole process. It's all captured in my book that I mentioned to you earlier on. So if we can actually characterize the shear strength of the soil, then we can prove that arching actually exists. Then if we can prove that arching actually exists, we can help the contractor to lower the jacking forces. With a longer drive, we have lesser number of shafts, we save on materials, and we save on resources. Okay, so that was the outcome of the pipe jacking method. By the way, this research is still ongoing, even though I'm in Australia, but my ex-PhD student now has taken the lead of this work, and I'm advising them on the new information. Okay, quickly, this is a case study 2. It's between Swinburne, Keller, the National University of Singapore, and Griffith University, where we use the same method. Okay, the power law as well as the tangential generalized method, again, to actually prove that this method is really reliable. So in this particular problem, this problem is in Vietnam. This is an international contractor. You can Google them. They do a lot of ground improvement. They are from Germany. They operate in Malaysia, Singapore. A lot of ground improvement works here in a tunnel, the KV MRT. They have a strong presence in Malaysia. So we collaborated with them. So in this particular case, we are working in a very soft soil, and this gives us the opportunity to build stone columns. Stone columns, like what I've said, is just pushing under a high pressure vibro, push the stones into the ground, replacing the soft soil, and then you have a cylindrical of replaced columns. So these columns are using 75 millimeter aggregates. Anywhere from 25 to 75 are acceptable. As you can see, this is the particle size distribution of the materials, and then because we have to sculpt the material so that it can go into the direct shear box, so we sculpt it to be this. This is perfectly allowed in the ASTM standard 2003. So these aggregates are microtonalite, which is granitic in nature. So we sculpt them according to the requirement of STM. We put them into the shear box, and then the contractor carried out the configuration that they wanted to test. So in this case, this is a plan view. You can see these are stone columns. Okay, column, stone column, stone column, stone column. As you can see, it's a different spacing with a capping beam. And then this is a cast tree. They stagger the length. You have got a shorter length, full length, and also a shorter length here. And we try to actually find out more. Okay, and then in this one also, we produce a lot of results in the American Society of Civil Engineers journal. We do a 3D model, and then we try to validate the outcome. So quickly, let me just show you the results. As you can see here, is the same method of how we actually do the direct shear box. We use back the same parameter or the same technique, using the power law and the generalized tangential approach. And then we did a parametric study. So if you were to notice, this dotted line here is actually the field measured results. And then the all these lines that we have actually got here is actually done through the finite element model, as you see here. Okay, so we measure the real life performance. You see there are jacks, you put the load on top, and then you jack against it, it pushes down the power. That's why you measure the real life load. So with the load settlement, that's what we get for the dotted line. And then for this, the one that we measured, then we can actually study the effect of dilation angle, because the rocks are actually pushed together by the vibro under very high pressure. So it gives the rock the opportunity to dilate when you actually try to shear it. So that's what my philosophy is. I want to prove that dilation angle exists under a highly compacted aggregates. And from this exercise, I managed to prove that, because if you don't put friction angle, your numerical analysis will not match what you actually measured on site. And you try that with different friction angle. Friction angle 30, friction dilation angle 0 still does not match. You do a parametric study, you try 35, and the dilation angle is 5, it still does not match. And then you try friction angles 40, and then a dilation angle of 10 is almost there. You can see you even try the cohesion, it's not very sensitive to cohesion. So what it means that granular material is when you put them under high energy, it's not very sensitive to cohesion, but it's very sensitive to your friction angle effect. So the one that finally match is that when your friction angle is 50 and your dilation angle is 20, you see you almost get a perfect match of your numerical model against your site reading. So from there, we managed to say that the influence of cohesion becomes less critical at a higher friction or a higher dilation angle. So the dilation angle is always a function of the friction angle. By knowing, if you know the friction angle from the tangential method or the power law, then you minus 30 degrees, that will give you your dilation angle. So from this, we managed to characterize the behavior of aggregates of at least 75 millimeter under very high pressure. So with that, we validated the concept that I just presented. And that's why I thought that I want to share this with you, because as engineering geologists, sometimes you want to work with the engineers, and when the engineers speak a certain language, we have to actually try to understand them, or the engineers or the geologists speak a different language, and we as engineers, we try to understand you. So that is when an interaction like this gives us a platform to actually share our knowledge. So in another 5 minutes, just allow me, Prof. Tan, another 5 minutes, I will just show you what our research group is currently doing. So we are, again, what you say, we are working a lot of aggregates on different geological formation in Australia as well. Again, we develop, now we improve we try to do a bit of higher end research. We try to develop a transparent shear box instead of an opaque steel shear box. We compact the material in there. And as you can see here, very delicate perspex that we do. We try to take photos of the interaction of the particles. As you can see here, this is a video clip. Let me see if I can actually play this. Why can't I actually play this? Okay, yeah, it's actually moving. If you can see this surface here. So we use the particle image velocity technique to actually capture the movement of the particle. Can you see? So this is where it's actually shearing against the concrete surface at the bottom. Okay, and then we try to take photos, and then we see how the particles will interact. And this gives us a lot of micro perspective of the interaction. Okay. So I just want to move on. So from there, from the image processing, we can actually study the movement in terms of our vector, and then we can actually understand how the interlocking of the particles would affect the strength development in terms of shear stress and displacement, as you can see here, how the interlocking would engage, and then how the interlocking would break, and then how the materials will roll on top of one another. So that's why we can actually explain the various curves according to their stages of shearing. So this is a theory, literature review. This is the practical thing that we do in the lab. We could actually verify the original theory by using a more sophisticated method. So students love this. Students can appreciate how the soil particles would interact, and then that stimulate their learning. Okay, why my slide isn't moving? Okay, now all these are published in the American Journal. As you can see, we actually explain, and we still use back the power law method, as you can see here. The power law, and then we still use the tangential method depending on where we obtain or confine the materials. These materials obviously are confined at 100 kPa, 300 kPa, 500 kPa. So these are the normal stresses that we're interested at. So the technique is still being you see, we developed that in 2013. In 2019, we have been benchmarking it against many other methods, and it still works. So you can safely use it. And we now has gone into discrete element modeling. We try to model the particles, as you can see here. I think it takes a while to actually show this video clip. Why is this not moving? So we can actually model this. We can do what they call a digital twin, if you wish, of the shear box. Okay, so once this is another PhD student working on this. Okay, oops. Okay. And now instead of the sphere, another PhD student is actually scanning using electron microscope to look at the material, the surface, and then we try to build a scanned particle of 1 cent grain. We actually scan it, and we use the actual shape of the particle in our finite element model. So this is the mesh, a finite element mesh of 1 cent grain. This is how it looks like. We scan it, and this is a density of the mesh that we actually use in our simulation. Okay, you see, this is a real particle. And this is the scan mesh. And then we also try to 3D print the particle. Okay, so this is what you see. Once we actually scan the particle, we model it, we put it into the digital shear box, and then we run the whole thing in a simulation. Okay, so at the same time, we try to validate still using larger particles. This is a large diameter shear box. This is 250 by 250 millimeter, as you can see, because we want to benchmark what we model against the real life behavior. As you can see there, there's a large shear box. So we kind of like digital twin the whole thing. So we develop a process flow, and then the student finish out with his PhD to compare the difference if you use a sphere and you use a different the materials and how the thing would actually behave. And we found that there are certain parameters that would yield 30% difference, because the state of the technology at that time was people using spheres, because spheres are the easiest to construct. But we put up a postulation that spheres are obviously not accurate because you don't measure the jaggedness or the angles or the edges of the particle. The roughness is important, so that's why we scan the particle, and we can prove that it's actually for certain engineering parameter, there is a 30% difference if you use scan real particle against the spheres. So as you can see there, so that was the conclusion of his PhD, and the student has been awarded a PhD. So now we are developing artificial intelligence method to actually process the results and also project and also to predict the jacking forces. So I've got another student who has just graduated. So she has developed what do you call, a Bayesian inference method to actually do the predicting algorithm. So nowadays we are going into the AI. So we also want to try to develop AI within our own field, and we have found that it's actually showing a lot of promises. And we are very grateful because we are supported by the university, by the government, as well as by the industry. Okay, so in conclusion, I've just presented the very reliable power law and the generalized tangential approach that I want to introduce to my fellow engineering geologists. You can read more about it if you Google me. And the particle shape has significant impact on the shear strength. And also we adopt the realistic geometric extraction method. It gives us the very accurate mechanical response. And we try to prove that the micro-mechanical behavior of granular soils we study in the lab can be applied in real life. And nowadays we are also, like what I mentioned, we are going into deep machine learning AI technique. It's here to stay. We can't run away from it. And I think it's the responsibility of the university and researchers like us to actually push the boundaries so that we can see, you know, how we could actually improve techniques, giving you more reliable data, more interpreted data, and so that we can actually advance the profession. So new research areas that we are going into now is the recycled aggregates for pavement, fouled railway ballast, or even stabilized subgrade. So this is where my clients are supporting me in my research. So I'm happy to share this with you in the future. Hopefully we will be in contact again. So you can actually contact me, and if there's any question, I'm happy to answer after this presentation. So another acknowledgement to all the clients and all the research partners who actually supported this research. And I really appreciate your support. Thank you.
Okay, thank you, Dr. Ong. Very interesting presentation. I see you have done a lot of work.
Yes.
Yeah, a lot of work. Yes. Yeah, based in the university, you do research but apply to industry. Very useful, I'm sure. Yeah.
That's
Okay.
correct. That's right.
Right. Now we open for questions. We start with the floor first. Any questions from the floor? You can just talk directly, yeah. No need to use the chat. You can just ask your questions directly to the speaker. Right. Anybody wants to start? I will have to call the members of the audience. Mr. Robin Liao, you are there, right?
Yes, I'm here, and
Okay.
I'm happy.
Yeah.
For this.
You can start the ball rolling.
This is, but I think Dr. Halim has a question in the chat box.
Oh, is it? Okay.
Yes.
Dr. Halim, you are there?
In the meeting chat, he typed a question.
Hello.
Yeah, you want to ask your question?
Yeah, my question. Okay. Hello. Yes, Dr. Dominic.
Yes.
Okay, my name is Dr. Halim. Actually, I punya PhD in soil mechanics. Okay. That means I punya research more to soil, plastic soil. Plastic soil. That means the PI is more than 40%.
Yeah.
Okay. Plastic index is more than 40%.
Yes.
Okay. Is it your model, power model can use for this type of soil, especially quaternary deposit soil area more, because I have one job at more area. That means they use the tunnel. They do tunnel to cross the highway from at more area. Because the issue is now, if the soil is homogeneous, that means cohesion is a maximum shear stress. And the friction index is zero. That is my question: how to answer, how to solve the problem due to two type of this parameter.
Yes. Thank you, Dr. Halim, for the question. Yeah. Okay. I think because you see, it depends on what parameter you get. If you get the undrained shear strength, so the undrained shear strength, you get it through the vent shear.
Yeah.
So the undrained shear strength will only give you the undrained shear strength CU value, right?
Okay.
So you have to actually, instead of the vent shear that you do in situ, you may have to actually extract the sample and do triaxial cell. Triaxial testing. Why do I say you do triaxial testing? Is because you need the C dash and phi dash.
Okay.
Yeah, because the vent shear will give you CU. The triaxial will give you C dash and phi dash. So you cannot mix these two.
Okay.
So once you get the C dash and phi dash, then you can actually use the tangential and the power law method. Because when you do the C dash and the phi dash, when you do it at various confining pressure, depending on the problem or the project you have, you do it defining different confining pressure, then you can actually get the scatter. Once you get the scatter, then you can actually also fit a power law curve to it. You see, so it very much depends on what you need, because in soft clay, usually people do vent shear and they get the undrained shear strength value, right?
Yeah.
So you cannot use power law on vent shear result, but you can use power law on the C dash and phi dash. And how do you get C dash and phi dash for soft soil? Is actually through the triaxial test.
Okay, that's clear lah. The issue now that maybe we want to increase the friction angle of the soil. How we solve the problem is
correct. So now you go into ground improvement. Because the soil is weak, you have to make it stronger. So usually there are two ways. Either you do deep cement mixing, which means you mix with cement, or you do the stone column.
Stone column, that means we use the water jet.
Oh, that is probably, if you say water jet, then I know what you're talking about. You are talking about jet grouted piles, is it? JGP.
Yes, water jet.
Yeah.
That means they have two types. One type is stone column. Maybe another type is sand column. And third type is with drain.
Yeah. So what do you intend to do? What's the project about? You said tunneling just now?
Tunneling, because the tunneling, the size, I forgot the size, because they do the tunneling, they add more area. Okay, they mean they do tunneling from the left to the right and past the highway. The issue is how they want to control the settlement when they pass the highway.
Yeah. So are you talking about a road tunnel, or are you talking about like what I talk about here, like a pipe jacking or a micro tunneling?
Micro tunneling.
Okay. Yeah. So micro tunneling in soft soil is also doable because it's easier to do it in soft soil than in rocks. So like what I said, sometimes if it's not very deep, then you can just actually jack through it without ground improvement. You see, so because it's soft soil, then I understand your concern, which is the settlement. So settlement around it would happen. So if you think that settlement would affect the highway, then yes, you may need ground improvement. Because once you actually do ground improvement, the soft soil will become stronger. And then when you actually jack through, then it will not settle as much.
That mean maybe we do the grouting first lah.
Yeah, of course. You have to do the grouting first. After that, then the micro tunnel would actually come through, and it will be able to crush the jet grouted piles.
Okay.
So once you actually do the jet grouted pile, then you can actually do a triaxial test. Then you get the C dash and phi dash at different confining pressure. Then you can actually use your power law.
Okay. Okay, clear. Okay. Thank you.
No problem.
Thank you, Dr. Dominic.
Thank you.
Can you give your email, or I can send maybe next time? Maybe I have some issue because I do a lot of work at the Sogran area. Okay. Maybe you give the email or whatever.
Okay.
Is it possible? Give to me.
Yes, I can give it. I'm tapping it.
Yeah, type it to me. Okay.
You can type it.
Okay.
Okay. Right,
Okay. Thank you, Dr. Dominic. Thank you very much.
Okay, no problem.
Right. Okay. Next question. That sounds a bit like consulting, huh? Just now. It's okay. Education is free, lah. Education is free. Yeah.
Yes. Happy to share. Whatever I can share,
Yes.
I will share.
Okay. Education is free. Yeah. Right. Next question. Still very quiet. Our audience, as usual, our audience usually is quiet. So I will have to go and seek the audience to ask questions. Mr. Robin Liao, you got question?
Okay. Thank you, Professor Tan. So congratulations again. Managed to organize one webinar very late in December. Maybe this is the last webinar GSM IGM going to hold, as I can see it. So thank you very much. So Dr. Ong, I'm very pleased that you are in Kuching now. Because I heard Queensland is being hit by the cyclone, the Jasper cyclone.
Yes, in the northern Queensland, where it's actually tropical, yes, it's actually facing the brunt of the cyclone. So luckily, also Brisbane is actually on the southeast corner of Queensland, which is subtropical. So we don't get much of the cyclone. So it's the northern Queensland that actually face a lot of impact from the cyclone. You are right.
So they say the cyclone will hit Cairns.
Yeah, Cairns is all the way up north.
I think Cairns is more than 1,000 kilometers away from Brisbane, is it?
Correct. That is right. That is right.
So subtropical. So the cyclone will not come to you.
Yes. We will get the tail of it, but not the full brunt of it.
That's why I was scared. If the cyclone hit, then we're gonna no webinar today.
Yeah, that's right. I'm in Kuching, so like what you say, I'm grateful to be in Kuching, but over here every evening it rains also.
I see. Okay. Second thing, I was expecting a Queensland geology because you are based in Queensland.
Yes.
but now Kuching. So I'm happy also. Kuching geology, happy. Okay, Dr. Ong, you were saying, your work is very great to begin with. This pipe jacking technology, then the stone column, and then your research work you're doing now, using the 3D print on the particles.
Yes,
that's amazing, man. And then using AI to do your jacking, to solve your jacking technology problem. and what they call this shear box, transparent shear box.
Yes.
Amazing. And recycle aggregate for your work, for your
Yes.
pavement. So congratulations. And you were saying you were the first in the world to work with this pipe jacking technology.
First in the world to interpret the granular material.
That's where your research.
Yes.
Power comes in. Yes.
Because in a lot of pipe jacking works, it has not gone so deep. So if you do not go so deep into the ground, you are dealing with soils. So because of the project requirement that is going 50-60 meters into the ground, so that is where we encounter a lot of rocks. And this is the first time in Sarawak or in Kuching that we have gone 50-60 meters into the ground. So the client is a joint venture between a Malaysian company and a Japanese company. Because of the challenges in the interpretation of the geology, they made the wrong tunnel boring machine on the first attempt. They said that, oh, your RQD is 0. But when they put the TBM into the ground, they cannot even move because the feed light was so strong. So how could this be RQD 0?
Yes. Yes.
So that's how it started the conversation. And I'm very lucky that I'm at the right place at the right time to engage the industry, and they also fund me a little bit. So I got good students. We got Final Element software, and a lot of people trust me in the work.
Yes.
And this gives me a lot of opportunity to work on things that have never been done before.
Yes. That's a very good. Congratulations, Dr. Ong.
Thank you.
By the way, now we are speaking about Kuching. So your deepest tunnel would be 60 meters, you see?
Yeah.
Okay, 60 meters. And you were tunneling into this field line, which is a weak rock, and it has a surprising property, even though RQD is 0, but the rock still managed to hold.
Exactly. Yes.
It's highly fractured, but it's managed to hold.
Yes. So
and
that is why
you can put a grouting material to hold in the tunnel.
Yeah, it's just suspension, bentonite to smoothen the pipe jacking process. Yes.
I see. So you can push in the concrete in.
Yes, that's right.
I see.
Like this,
Yes. By the way, Dr. Ong, I understand that Kuching, there's also a lot of peat.
Yes.
And this peat, it give off methane. So people have problem with the peat in Kuching. So do you encounter peat in your work?
Yes, I do. When I was based in Swinburne for 11 years between 2007 and 2017, I did a lot of work on peat as well. Yes. So, but the thing that you mentioned about peat giving out methane is that because most of the peat here is actually the peat swamp, and it's always wet. So, and it does not always catch fire. So the release of methane is not that widespread, but it's more towards construction problem, where they try to actually construct on peat. I just went to Cebu last week to see some of my projects that I did when I was based in Swinburne. So and I look at all the projects, they are doing well because you know, when we design in peat, we got to make sure that the structure is strong, and then the characterization of peat plus soil is actually correct. So yeah, I actually do quite a fair bit of work on peat as well.
So good, Dr. Ong. So you done work on peat. I'm curious to know how thick is the peat there?
Now in Cebu, the pit can be 15 meters, 15.
Okay.
And the moisture content can be about 1,000. You know, it's a very homogeneous peat.
Okay. In Kuching, any idea?
In Kuching, it's not as deep as in Cebu. In Kuching, we have pockets, let's say in Batukawa, in Matang, you know, but in Cebu, it's basically the whole town. You see, so it's a different scale. It's a different scale of the distribution of peat between the Kuching peat and also the Cebu peat.
Okay. So thank you, Dr. Ong and Professor Tan. Thank you for organizing this webinar again.
Okay, you're welcome. You're most welcome. Okay, we still have about 5 minutes. Any other question from the audience? Some of them are regulars, but they never ask questions. Anybody, any takers? We still have 5 minutes. Okay, if there are no other questions, I will just ask a couple of short questions, Dr. Ong.
Yeah, sure.
First thing is, you tested the crushed rocks, the rock spoils and all that, as a soil, as sand or gravel, right? It's crushed rock.
Yeah.
So your result is like results for sand or gravel soils. Yeah? Whereas when you do your pipe jacking, you're actually dealing with a rock mass, right? You're jacking it through a rock mass. So is there a problem? Is there some kind of it's not quite correct? I mean, your test results are.
Yeah, so that is why if you look at the language that we use, we actually call it the equivalent parameters. So that is why we put up the postulation that even though it's actually reconstituted, but at sufficient high pressure, that the reconstitution of the particle would act like somewhat like a mass. So the equivalent of it is what we actually try to characterize. So you can actually think of it as the lower bound parameters. So that's why we call it as an equivalent parameters. We don't call it as the actual parameters. So in this case, we found that for all these materials, if we manage to confine them under, as you can see, we did 100, 200, and 300 kPa confining pressure. The effect is somewhat on the lower bound of the original rock mass.
Okay, but there would be a slight difference,
we
the original rock mass.
We acknowledge that because we mention it as reconstituted. We mention it as equivalent lower bound parameters. Yes.
Yeah. The other comment is the table on the different parameters for different rocks, right? Phyllite, shales, and the overseas publications and other rocks. Actually, I mean, in geology, phyllite, there are many types of phyllite, just like granite. They're all kinds of granite. So in your case, when you do an actual project, you will have to test that rock or the reconsidered soil from that rock. You can't apply generally say your phyllite, these are the values, because another spot, say in Kuching itself, different phyllite would give you maybe different results.
Yes.
So you have to conduct tests, right?
Correct. That is correct. Because in this work that we do, we are limiting the work here to Kuching phyllite. So Kuching phyllite, you know, this thing about metamorphic phyllite is actually abundant in Kuching, but it's not found in many other places in Sarawak. So in our work here, that's why in all the journals that we write, we are very specific to say that this is actually a Kuching geology, and we even call out the formation. So the phyllite rocks typically occur in the Tuang formation of Kuching. Yes, so we go to that depth to help people understand that it's a localized kind of a rock formation.
Yes. Just like in KL, we have the famous Can Hill Formation. Part of it is phyllite also. It's phyllite and quartzite. You know, the Can Hill Formation. Yes. But that phyllite will be much stronger than your phyllite in Kuching.
Yes.
So you cannot apply as a rock type. Cannot apply, like you have to test individually.
Yes, exactly. Yes.
Okay, the last comment, very quick one on the RQD 0 is actually very misleading on the strength of the rock.
Exactly.
RQD is based on rock cores that are more than 4 inches, 10 centimeters long. Only rock cores that come out, they are more than 10 centimeters will be counted in the RQD. So of course, in your case of phyllite, it's so fractured, the relations, so you will never get 4-inch core. So they all shorter than 4 inch. That's why the RQD is 0. Actually, the rock material is very strong, right? Because it's a metamorphic rock. Okay, that's my last point. Okay.
Yeah, so to add on a little bit on that comment, that is why after the project, we really recommend to the contractor to actually do a pressure meter test, in situ pressure meter test, to test the rock mass as it is in the ground.
I think that's the best, actual field test of the strength.
Exactly. Yep.
Okay. Any last question or last call from the audience before I close the seminar, the talk here? Anybody? Last question. Last call. Okay. It looks like none. As usual, our audience they are very quiet. Many of them attend. Many of them.
If you think of any question, then of course you can send me an email.
That's right.
I've already posted my email there. Happy to participate in this webinar. Thank you, Prof. Tan, for having me here.
Okay.
Prof. Tan.
Yes.
Even though the participants are quiet, but they really appreciate the presentation.
Okay, good.
They really do, yeah.
But I wish they will ask more questions, because the idea is this is not a one-way street. It's not from speaker.
Yes. It should be. It's a learning process.
Interactive. And if you have any doubts or any question or ideas, you can always bring it up. Like I mentioned before in one of our talks, you know, when I first went to America, my first lecture, after the Masaleh professor gave a lecture, so he asked, any questions? Every student was quiet. Everybody is, very quiet type. So straight away he said, "Oh, ask questions. There's no such thing as a stupid question. Anything you want to ask, go ahead and ask. You don't feel shy or you don't be afraid that it is a stupid question, something like that. Just ask. Okay."
Yeah, okay. Prof. Tan, that is so true. So true.
Yeah. Okay.
The question is the question.
Right. Okay. With that, we close the seminar, the talk, by thanking our guest speaker, Dr. Ong. I think he has done fantastic work for a very relatively young man. He has gone very far. He has raised the bar very high, and now he's doing research from Australia, right? Griffith University. So my best wishes to him. Good luck in his future research and all that. And of course, he's also doing consultancy work. I'm sure, right? Start from Brisbane.